Okay, wait a minute. Okay. So, okay, I start a little bit for the recording. So for the conservation of mass, we are dealing with the three-dimensional. So we assume that our molecule here is in cube shape. So we have an x-axis here, z-axis, and y-axis here, and then the length of this cube can be determined as dx, dy, and dz. So the idea is dy here, dx here is a small portion from the x-axis, and also the dy and dz here. So to derive the continuity equation, we are using a basic idea of mass flow rate. So we could write as m naught here, m dot here, and it is equal to rho AV, which is the rho is the density of the fluid flow, and A is the cross-sectional, and the V is the velocity. So to simplify to start our calculation about the continuity equation, the conservation of mass, might be we could start with this simple 2D diagram. So we have a square here. So we have one input for x-axis and one output for x-axis, and another one input for y-axis and one output for the y-axis. So for the inlet here, so we write as rho u dy dz. As you could see, the equation is actually reflecting the rho AV. So the rho here is the rho, the density of the fluid. Dy dz here is the A, the cross sectional. So this is dy, and the width here, which is normal to the screen, is the width. So dy dz is the cross-sectional area, and the V here will denoted as U because the velocity is velocity at x-axis. So for the outlet here, so it remains the same equation, which is rho AV. So the most obvious one is the dy dz, which is the A, the cross-sectional, because we assume that the cross-sectional at outlet here is remain constant, which is similar with the cross-sectional at the inlet. However, for the rho and V, at this situation, we are discussing about rho and U. For rho and U, we are writing in this term, rho U plus del rho U over del X, because we need to use the partial differential method. Because the idea is we have density and we have velocity. We have possibility to have constant density and changes in velocity, or we have constant in velocity but changes in density, or we have both conditions, mean density and velocity keep changing. That's why we write about rho and V here by using the partial differential. So mean the rho U is the previous value of density and velocity plus del rho U over del X, and dx is the changes for the x-axis here. So the idea of del rho U over del X, also I hope you could refresh yourself about the differential, the partial differential. So it can be right like this. Okay, wait a minute. So for the partial differential, I hope you could remember the idea of del rho U over del X, and it can be right is we have a constant density, and then we have del U over del X, and then we plus with, we have a constant velocity, and we have del rho over del X. Okay, so that's why we write about the, the output here by using the partial differential, because sometimes the density might be constant. The change is about the velocity, and then we add the changes of density and we constant the velocity here. So the idea of this one is, can be said, the general idea is, might be the changes is 20% from the density and 80% from the velocity. Okay, the same idea goes to the y-axis here. So we have rho v dx dz. So this is dx and dz is the width. So this is the cross-sectional area. The v here is the velocity for y-axis, and the rho is the density. And then we write the same ideas of in the outlet here. So we have rho v plus del rho v over del y. dy means changes at dy at y-axis, and dx dz is the cross-sectional area. Then we need to calculate the net flux of mass entering the element. It can be written as m dot for inlet minus m dot for outlet, mean mass flow rate for inlet minus mass flow rate at outlet, and it must equal to del mass over del T. Means that the changes for inlet minus the changes of mass flow rate at outlet must be equal to the changing of mass over time. Okay, so what is this element means? Okay, so for example, okay, so the basic idea might be we could a little bit tone down the idea of dm over dt. So let's say we have something like this. So we have a very closed compartment, the one system here. So we have a mass flow rate at inlet, and we have mass flow rate outlet at outlet. So the most common situation is we assume that this system is filled by incompressible flow, and the fluid is already filled all the volume here. So mean because it is incompressible, it cannot be compressed. So everything that goes in must equal to the everything that goes out. So in the very simple situation, we could see, we could write that mass inlet must be equal to mass outlet. So this is the basic idea. So for example, if you have one system filled with water, so if you give 1 liter, so for sure you will need to take out 1 liter from the outlet. If not, the system will burst, will fail, I mean. Okay, so then in this situation, actually, if we try to link this idea to this basic equation, we could write as m dot in mass flow rate at inlet minus m dot out, mean mass flow rate at outlet, is equal to dm over dt, which is equal to 0. Why dm and dt equal to 0? Because we believe that the changes of mass mean that the increment of mass over time in this system is equal to 0. Okay. Yes, we have mass flow rate at inlet, and we have mass flow rate at outlet, but the mass here is not changing over time. So dm dt means the changes of mass over time, as we have dx dt and so on and so forth. So I think you could start to understand what is the meaning of dm dt. So dm dt means the changes of mass inside this system over time is equal to 0. So means that that's why we simplified as mass flow rate inlet equal to mass flow rate at outlet. But actually, we are using this basic equation. So this is the very basic idea. Then, okay, so we have sometimes have system like this. For example, we are still dealing with the incompressible situation, incompressible system. For example, we have a tank here, and then this tank is half full, and then you give the mass flow rate inlet here, and then you have a mass flow rate outlet here. But might be, okay, to make it a real situation, might be for the outlet here, you just install a small pipe, but the inlet here, you install the bigger diameter of pipe. So means that the mass flow rate is bigger than the inlet one is is bigger than the outlet. So for sure that it has increment of mass inside this system. So we cannot just use the idea of inlet equal to outlet. What we need to understand is mass inlet is equal to the mass outlet here plus to the changes of mass inside the system. That's why we need to write m dot in equal to dm dt plus m dot for outlet. So, and then we rearrange this equation. We could have m mass flow rate at inlet minus m mass flow rate at outlet equal to dm dt, mean d dt or changes of element over time. Okay, so it comes from the it's come from the previous scientists. They start to have they start to think to produce one simple equation that can suit for all the situation. Okay, then we have another ideas. So we are dealing with the compressible flow. So for example, we have here, we have the compressible flow system. Compressible might be we are dealing with air, gas. So you have the mass flow rate at inlet. So the gas will push into the compartment here, a vessel here. And then you have one outlet here. So might be for compressible flow, we could say it can be both. It can be m dot in equal to m dot outlet out. Okay, so we take the a little bit not common situation, which is the normally for gas the mass flow rate at inlet is not equal to mass flow rate at outlet. So what happened, because the gas inside the system might be changed. The mass mean there are increment of mass inside the system. So we write m dot in, mass flow rate at inlet is equal to changes of element inside the system plus mass flow rate at the outlet. And again, the idea of this one can be rearranged, and we could write m dot inlet minus m dot outlet equal to dm dt. So means that this is the basic idea how to remember this equation. Okay, this final idea for incompressible and compressible flow. Okay, so we go back to our calculation here. So the idea is, please remember this one, and then we are going to substitute all the information that we have from our schematic diagram here. So for mass for inlet, so because we have two inlet here, so we have inlet for x and inlet for y, so we could write as rho u dy dz plus rho v dx dz, and then we have two outlet, so and then we sum all the outlet here by having minus rho u here and another minus for rho v here, and then it is equal to d dt for mass. So for d dt for mass, first we write del d dt or del over dt, and then for mass here we write as rho and v. Okay. So here, please remember that the basic equation is we know that we know that rho density is the equal of mass over volume. So, and then if we want to calculate the mass, we could write mass is equal rho times volume. So that is the idea. So we use rho. So this is rho, the density. So the density is rho here, and this is the volume. So the volume means the volume of this system. So we multiply dx times dy, and then we times dz, the width, which is normal to your screen, as the volume of the element. So, and then if you simplify this one, so I hope you could do this. Okay, if you solve this equation, and then So finally, you could write as del rho u dx plus del rho v dy plus d rho dt is equal to 0. Okay, and then if we want to add the value of z direction, so we could simply add del rho w. So rho is the density and w is the velocity parallel or the velocity on the z axis, and then over dz, and then we equal to 0. So I hope you this is the very simple idea. So we could add from the basic equation here. If not, you could do same thing from the three-dimensional diagram. So and then what we need to do is we need to we need to multiply the value of this one. So we have del is the partial differential. So we need to enlarge this one. Okay, so del rho u over the dx will become del rho, it's become rho del u over del x plus u del rho over dx. So I hope you could remember the idea of partial differential. So for example, we have del rho u over del x. So we could write it is equal to rho del u over del x and plus u del rho over del x. Okay, so this is the idea about this one. So okay, if you do this thing, you could write as this one. Okay, so this is the differential continuity equation that you need to understand. So and then it's depend from the textbooks. Okay, in the textbook it's depend on the situation, but in our case here in our class, so we are using the longer equation of continuity equation, because in many textbook they will simplify this one because they are dealing with incompressible. So the incompressible means the density of fluid is not changing. So means that from this equation means there are no the density here is constant. So means we could bring everything in. So the rho here is constant, and there are no d rho. There is no del rho here. Means del rho dt means the changes of density along the time. D rho dx mean there are no density changes along the x-axis, along the location of x. And also there are no density difference between in y-axis and no density changes in z-axis. So if because the density is constant, so it could write like this. So why the rho here is disappear, because we could bring the rho to the right hand side here and it will become 0. Okay, because rho is cannot be 0, so the 0 is must be come from these terms. So we could write this one. And then again, if your problem is in two-dimensional, so meaning we are not dealing with there are no z here, so we could say that dw dz mean the changes of velocity for z-axis along the x-axis is remain constant, so it become 0, mean no changes at all. So it becomes 0, and then it can be simplified as this one. So this is the idea of Cartesian coordinate. Okay, so this is the notes. So, but I think I hope you could know how to write this one, because all our calculation is using the 3D axis here. Okay, so this is the equation. I hope you could print screen it. Okay, now we are focusing on Navistore equation. So we are for the next notes. Okay, I will show you about the polar coordinate, but for now we are focusing on the Cartesian coordinate first. Okay, so the Navistore equation is actually the momentum equation, or we are you could think something like this. Now we are we try to derive an equation to solve problem for moving fluid, because continuity is the one equation that could help us solving that one, but the continuity equation doesn't have uh, it's not derived from the idea of force. So as you know, when something moves, it will create force, because force is equal to momentum. It is equal to the x, this with F equal to ma, and so on and so forth. Okay, so the Navistore equation, it widely used in fluid flow, and then there are multiple ways to derive the Navistore equation. And then what I'm going to show you is actually the very simple derivation of Navistore's, because I might be show you some jump, means I not show you the detailed ones, because the Navistore equation is actually very detailed, because we are at least you know how Navistore equation has been derived, and we are focusing to use the Navistore equation actually. Okay, you may found the notes from how to derive Navistore equation in YouTube. There are so many about that. So it took so long, because if you are going to solve matrix, okay, so at least we have around, if I'm not mistaken, it is around 32 unknown parameters that you need to solve it simultaneously. But okay, I'm skip about that. Okay, so we are going step by step. First, okay, you need to understand that we need to select our fluid particle. So we select one particle in a flowing fluid, in a flowing fluid. So we imagine that the particle has a shape of cube like this. So, and then to simplify our calculation, we just imagine that the length of the cube is delta x, delta y, and delta z, because we are going to analyze this in three-dimensional. So, and then you assume that the flow coming from left to right, something like here. Then the second one is we start with the Newton's second law. So mean we start with the force. So and then we think, okay, we assume that there are two categories of forces, which is the body forces and the surface forces. So body forces mean force that come from the body itself. So mean it's the weight of the molecule. And the surface forces is forces that comes from the fluid that go through the fluid. The forces that maybe exist when fluid flow around the particle. Okay. So because the existence of surface, as you know, we have sometime when fluid flow, it will create pressure. So when the pressure exists, at the same time you have surface, so mean pressure times area will create force. Okay, then if you have fluid, for sure you have shear stress. Then when you have shear stress, for sure it will react, or the idea of no slip condition will be occur. So mean that shear stress will stick. Okay, why shear stress exists? Because shear stress will stick on the surface. Okay, and then the idea of shear stress times area will create another force. So that's why we say that the surface force means force that exists because you have surface. Okay, is actually the pressure force and the shear force. Okay, shear force is about the shear stress, and pressure force is about the pressure that occur on at certain location. And the body force is actually the weight. When the gravity try to pull the molecule down, so means it has force, which is the gravity force, or we call it as a body force here. Okay, the main idea to calculate the force is F equal to ma. So the idea is m is the mass and the a is the acceleration. So, and then the total force that occur in this situation is body force plus the surface force. So, which is equal to the mass times acceleration. So, we could simplify, we could expand the equation for mass. So, we write rho times volume. So, this symbol is for volume, as I previously explained. And then A is the acceleration. Then we could write all the sum of the forces here. So we have the body force, which is the weight, the force that comes from the pressure, and the force that comes from the shear stress. And then we have rho and we have volume here. And then we expand the idea, the terms of acceleration into dv dt. Okay, in this derivation, so for if you look, there are so many derivation that you face before and after this class. Okay, might be in other subject. So in mathematics, in physics for mechanical engineering, we found that it is sometimes better for us to expand the second tier or third tier equation. So for example, mass is actually the multiply of rho and volume. So it is better for us to use rho and volume, because if we keep using mass, might be we have a problem because we don't know. Might be the rho is changed but not the volume, or the volume is changed but not the rho. So the mass is keep changing, but we don't know which part is constant and which part is changed. Okay, it's same with the acceleration. So it is better for us to use the velocity, because the velocity is the idea of length over time, and we have another time here to make it a acceleration. So if you see this acceleration, the unit is m over second squared. So it means that it the second tier terms. So second tier means you have one term, but in that term, in the second tier term, there is another term. So means it is not easy to see the changes because you don't know the basic element on that term. So that's what I'm going to tell you. Okay. So means we expand everything. So we have the very simple one, this one. So, and then for the weight here, we change into the mg, and then we could change again the value of mass here by rho, volume, and gravity. So we write everything here. So this is the terms. So what we are going to do here is we try to get a term expression for pressure force and the shear force here. So we are going to calculate the pressure force first. Okay, for example, so this is our particle here, and then we try to take the center point as our reference point. That's why we could say that the pressure comes from the left to right is P, and then it's multiplied with the area here, and then it could create force. So, and another forces that act from right to left here, and we could write it is P times A. But to differentiate the value, the direction, and so on and so forth, in our textbooks, okay, if you see a common textbook about this, they will write x minus delta x over 2. So what is the meaning of this one? So the meaning is, so let's say we have a value of x here, so we need to for example, for example here, so this is the coordinate. So because we want to calculate the pressure at this point, So because, and then we simplified it to this surface. So the location of this surface is actually x minus the coordinate of x here minus delta x over 2. And then here is x, the location of x here plus delta x over 2. So this is delta x and this is location. So that's why the meaning of this one. And the idea of we have two forces react from left to right for this one and right to left for this one is the idea to get the equilibrium condition. So I think okay. So I simplified this one, okay, because I'm not showing you the calculation because it's going so because the main idea is to understand how the Navier-Stokes equation being developed. So for the pressure force, so the equal is pressure times area. So and then we have the pressure for minus for the left hand side, and then we need to minus with the pressure from the right hand side. We plus delta I over 2 is the right hand side. Why minus? Because pressure is scalar, but force is vector. So when you have force from right to left, so normally we give the negative sign. So and then we pull up the value of A here, mean the area. So A will become AX plus Y. So and then what we do is actually, if we do again and again, because we have so many surface. We have surface on X axis, we have surface on Y axis, and we have another surface for Z axis. And then finally we sum all the forces. So we could get the idea of this one, dP over dx for x, y, and z. Okay. So this is the idea of pressure force. So and then we could calculate it. So this is for the vector. So I simplify it. So we could say finally is the pressure force here is actually the value of pressure, okay, times the volume. So main times x, y, and z. Okay, so the reverse triangle like this. So del x. So this triangle is delta. Delta means the difference. So delta x means the difference or the small part in x-axis. But the reverse triangle here is actually nabla. Okay, you could search this in internet. So nabla has its own meaning. So nabla is actually the meaning of d dx, d dy, and d dz. Okay, please reserve the idea of nabla because I have notes for the nabla at the end of this chapter. Okay, and then after you see the note of that nabla, okay, you can understand the idea of nabla here. So nabla here is actually the symbol for d dx, d dy, and d dz. Okay, so if you have nabla p, so means that you have del p del x plus del p del y plus del p del z. So this is just the conclusion symbol for certain very long formula. So and then in physical interpretation, we could say that the gradient of pressure field at a point is equal to the total pressure on the fluid divided by the volume of the particle. So in two-dimensional, the pressure point, the pressure is pressure is also the force divided by the area. So that is for the two-dimensional. But for the three-dimensional, because we have the z axis here, so it will become force divided by the volume.